So when we now have AGX Unity installed, we can find a lot of things in the AGX Unity menu. For example, we can find all the available collision shapes that we support. So you can see there's a list of these collision shapes, and we can create one of them by just clicking in the menu. So here we get a box. We can see the properties for the box, so we can change the size in X, in Y, and in Z. There is also a size tool here, which we can use to scale the object in different directions. Now, it's really important that you do not use the scaling transform here that comes with the game object, because AGX Unity does not support non-uniform scale. So we try to avoid using this scale for any collision shape or any rigid body. Triangle meshes can be handled in a slightly different way, and we'll have a look at that later. We can also see that there's a few other settings here in the inspector. We can disable or enable collision for a shape. We can specify whether it's a sensor. We'll talk more about this in a later session, but it's about collision generated with a shape that is a sensor will not be handled as contact constraints. So the solver, and we will not get any impacts from the contacts, but we can use these contacts to trigger events, for example. So that's typically where you use a sensor. We also have a shape material, which defines the physical material of a shape. We also have render material, and that is for the visual representation of this object, which is created automatically when we use these menu options. So let's create a sphere. Same thing here. It's a mathematical primitive. It has a radius. We can also use the shape tool to change its radius. And we can see that it scales around different points. We can create other things such as a capsule, which is a cylindrical shape with two half spheres at the end, and they have a radius and a length. We can create a cylinder, which is also a mathematical cylinder with a radius and a height. Let's go on and create a mathematical plane, which defines an up vector and a down vector. So everything here is on the positive side and everything here is on the negative side of the collision plane. So there cannot be anything below a plane. We can create a mesh. A mesh is actually a kind of special object because it requires a source mesh. So you need to have a mesh on disk that you can use for defining the shape of the triangle mesh. Let's see if we have something like that. So here on disk we have something called a night.obe. Now there is one thing very important about meshes on disk and assets on disk which are supposed to be used for collision detection. And that is, you need to enable the read-write enable flag. So this flag needs to be set. So if it's not, you need to enable it and click apply. Now, if I would like to use the OBE file here on disk as a collision mesh, I can just select my mesh, open up the OBE file and locate the actual mesh data, and then drag that into source. So now we're actually using this OBE file triangle mesh as a collision mesh defined in AGX Unity. But right now we can't really see this. So if we would move this out here, there's nothing there. There is no visual representation of this. So either we can drag the whole OBE file into the scene, or we could actually use this tool here called Create Visual Representation of the Physical Shape. Meaning, if you have an AGX Unity shape which you have created by adding a component, you can actually click this and say, I would like to create a visual representation of this shape. So now we can see that we have a small, but it is a triangle mesh shape. Now we cannot simulate this because it's only a shape. We haven't added a rigid body. So to add a rigid body, you can do it in many different ways. One is to actually create the rigid body including a shape, or create an empty rigid body. So here we have an empty rigid body with no shapes. So we can see that, okay, it doesn't have any shapes. So then we can take this mesh, drag it in, so it becomes a child of this rigid body. Now we can actually simulate this, and it will fall down and bounce on this infinite plane here, this collision plane. So I also said that scaling is a kind of a special thing. If we select the mesh here, which has a reference to this mesh on disk, we can actually use scaling here. So if I would make this 10 times bigger, really large triangle mesh, like this, we can see that we have scaled the visual mesh and also the collision mesh. And that is okay for a mesh component. But it's not okay to select the rigid body and set scaling. That is not allowed. But a mesh you can actually transform, because we will read out the mesh data. So now we can see that it's being simulated exactly like we wanted. So let's move along. We have more shapes. We have seen mesh. We have something called hollow cylinder. Now, hollow cylinder is a category of what we call quadratic colliders. And those are used for mathematically very accurate collision detection. So, for example, a cylinder that fits into this hole here will have a very accurate collision detection. There's no tessellation, it's not a convex, it's a mathematical primitive. So you can actually fit this cylinder in a very good way into this cylindrical hole. So you can have a very tight fit and it will still be able to move around here. So that can be used, for example, to simulate peg in a hole scenarios. We also have more shapes, such as cone. Now, cone is a somewhat limited object. It's considered to be a convex object. We'll talk a little bit more about the difference between convex and non-convex object. But a cone will be treated as a convex geometry against all other shapes, except for cylindrical hole and something called hollow cone. So if we take this hollow cone and we rotate it 180 degrees like this, and we would also rotate this 180 degrees, something like that, we can see that, yeah, it can actually fit into something like this. Now, this one is not a rigid body. If we want to make it into a rigid body, we could do that by going here, create an empty rigid body, take the cone, add it as a child to this rigid body, and then start the simulation. And then we can see that we can actually see that this cone fit perfectly into this conical hole. So the whole purpose of these cylindrical hole, conical hole, and cone is that they fit very well together, including also the cylinder. Now, if we would switch and have a look at the available shapes that AGX Dynamics for Unity support, we can see that we get a matrix that defines the exact intersection tests that we can do. So, for example, a box and a box can collide perfectly. So everywhere you see a cross, we have a full collision detection generating robust and reliable contacts. As soon as you see something, a cross within a parenthesis, it means it has a limited function. So that's exactly what I said about cone. It has a very limited collision detection against other shapes, except for other cones, hollow cone, and hollow cylinder. But if we would, for example, take two planes, that's not defined. We don't have any collision for that, so it will not react at all. So those are mathematically not defined. We also have entries which doesn't have anything at all, and that means there is no representation for colliding a cone with a triangle mesh currently. That means we haven't implemented this feature yet. But we can see that most of this is actually filled with crosses, so that means we have a full collision detection. So if we go back to the editor, we can see that if we select the mesh, it also has some options. By default, a mesh will be treated as a non-convex triangular mesh. It means it can have holes and cavities and things like that. So this is obviously a non-convex object. For non-convex trimeshes, we can also do collision mesh reduction, meaning that if it has a lot of triangles, we can reduce the number of triangles that we use for collision detection. So by doing that, we can enable reduction, we can press the button apply, and we can do a more aggressive mesh reduction if we want to have fewer triangles. Fewer triangles means, in most cases, better performance when it's being used together with a triangle mesh. So we can undo all of that. But we can also make it into a convex object. And if I do that and hit apply, we can see that we have an algorithm that treats this non-convex object as a convex mesh. And if I start the if I do apply and I run the simulation, we can see that it now behaves completely differently from before. So that means it will no longer interact in the scene as a triangle mesh. Instead, it will react as a convex mesh. Now, there are some benefits of using convex mesh. The performance might be better. It's more robust in terms of finding out what's inside and outside of a mesh. But it really depends on the use case that you have. We can also use convex decomposition, which means that you can specify a certain resolution and the algorithm will try to fit a number of convex objects so that you retain the overall shape of the object, but now it's not represented as one triangle mesh. Instead, it's represented as a number of convex objects. If I use this for collision detection, we will get an overall behavior which is similar to the triangle mesh, but it's not the triangle mesh being used for collision detection. It's actually a set of convex objects. So now let's have a look at RigidBodies. So we can see that we also have a menu item here called RigidBody. And here we can create RigidBodies that is already populated with a shape. So we could, for example, create a sphere. And we get a sphere shape, but now it's also a rigid body. So if I start the simulation, we will see that this sphere falls down and it collides as a sphere with this ground plane. We can also see that as a rigid body, it has lots of parameters. It has a mass, inertia tensor, and it has a center of mass. By default, when this checkbox is enabled, we will automatically calculate the mass based on the volume and the density of the object. Same thing with inertia and center of mass. But we can also change this if we want to. So if we want to make it a really heavy object or a really light one, we can do that by disabling this automatic calculation. A rigid body can have 3 different motion control. By default, it's dynamics, and we could see that when we run the simulation, we see that the rigid body is affected by the gravity field and it will fall down due to the gravity. We can also add forces onto a dynamic body. We can add constraints to it and make it behave according to the constraints. So it can be affected by forces. If it's static, it means it has an infinite mass and it will not be affected by gravity or any other forces. So it will be grounded to the world. The third one is kinematics. It's kind of a special one. It means it has an infinite mass. It cannot be affected by forces, but it can react to velocity. So I can specify linear and angular velocity, and it will move along that velocity. So if I change the velocity to minus something like that, we can see that it starts to move in that direction. So we can use a kinematic body to animate motion. If we, for example, have an array of position and orientation over time, we can use that to control a kinematic body. So other parameters for a rigid body is motion damping. So if we make this rigid body dynamic again, we can add viscous damping, which works almost like aerodynamics or hydrodynamics, meaning that it adds some velocity damping to a rigid body, resisting acceleration. So here we can see that we have a very high velocity damping in the y direction. So this rigid body moves like it's moving through some medium. Now we also have other modules, including aerodynamics and hydrodynamics, that we will demonstrate later on. Further down we can see a list of the shapes that are attached to this rigid body. So all the shapes that belongs to this rigid body will be listed here. So we can access the sphere and we can change the properties of all the shapes here. We can also see a list of constraints. In this case we don't have any constraints, so it's currently empty. So we'll add those constraints later on. A third way of creating rigid bodies and shapes is to use the context menu here inside of the hierarchy browser. So here we can see that we can create a rigid body that includes a box. And we see that we get a rigid body with a collision shape, including a visual representation of the shape. Now, what if we would like to create a rigid body that contains more than one shape? What we can do then is we can go to select the rigid body here and go to AGX Unity, collide, and create another box. That will effectively create yet another box with a visual representation, and we can move that independently from the other one. So we can move that and we can rotate it and do everything that we want, but it's still a child of this parent rigid body. So now if we look at the shapes, we can see that it actually has two shapes. So if I would start this simulation, we would see that these two boxes would react as if they are part of the same rigid body, which is exactly what we wanted. Sometimes it's very useful to be able to interact with the dynamic scene for debugging and for testing. So we can do that by looking here at the AGX Unity settings. We can see that we have something called pick handler, and it's currently bound to the keyboard key A. So if we press the keyboard key A and use the left mouse, we can interact with objects using a spring model. So here we can see that if I press A and use the left mouse button, I can lift up and I can interact with objects. It only works for dynamic objects. So you can see that I can't use this for static objects, or basically shapes that doesn't have a rigid body or rigid bodies that are static. But anything that is dynamic, I can pick up and I can interact with like this. Another very useful tool is to use the Debug Render Manager. You can find that here in the menu, AGX Unity, Managers, Debug Render Manager. So what you can see here is that during runtime, you will get a visualization of all the rigid bodies that has a shape. Now, not only that, but you can also see the contact points that have been generated from the collision detection, and you can scale them depending on how large your scene is. If we enable colorized bodies, each rigid body will get its different color. So we see that all the shapes belonging to a certain rigid body will have a certain color, so we can differentiate between different rigid bodies. We can also enable this highlight, so that if we hover over a shape, we will see that shape being highlighted. So this can be very useful when you are debugging your simulation. And if you would like this to be included in your build, you can click this and it will also be part of your build later on. If you just want to disable it, then just disable that component and it will not be visible anymore. Whenever we start a simulation, we can also see that there is an object automatically created called AGX This is the object that actually has a reference to all the shapes, the rigid bodies, and all the constraints and everything going on in the physics engine. So we have lots of parameters here that are relevant for the simulation. But if we want to set those parameters, we need to create a simulation before we start. So we can do that by creating this simulation object. So we have a game object here with a component simulation. And now we can actually go in here and we can change the gravity to 0. We can start the simulation. And then we suddenly see that, oh, there's no gravity here. So if I interact with an object, it just continues as if there were no gravity. So we can change this to 9 or something similar if we want to again. We can also change how the simulation is being stepped. Now, by default, everything is being stepped according to Unity's fixed update stepping. And that means we cannot change the physics time step here. We have to do that in the project settings. So if we go to project settings, we look at time, we can see that we have a fixed time step. We recommend if you use this, you should have the same fixed step for maximum allowed time step also. So here we're using 50 Hertz as a time step, so 0.02 seconds. So this is what's being reflected here. If I want to change that, I have to go to the project settings. Now, there is another way of doing the stepping. That is to use our own stepping callback. That means you can actually change the time step to anything that you would like. And what happens is that during a fixed update, there will be multiple calls to the physics update. So here we're running in 100 Hertz instead. But what happens is that for every time step Unity wants to step, it will call the physics 2 times. So we run the simulation in 100 Hertz. So if we change back the gravity to minus 9.82 and start the simulation, we can see that it behaves just like before, but now we're using 100 Hertz time step. We can change that to 1000 if we want to, but then it will be very hard to catch up and get the real-time simulation. But this means that you can separate the Unity time step and the physics time step if you would like to. We can also use the simulation component to display statistics, and they will actually show up in the game window. So when we start the simulation, we get a window where we can see how much time is being spent in the different parts of the physics engine. We can see that we have collision detection, we have the solvers, and the overall time being spent inside of the physics engine. We can also get some statistics about the time step and how many rigid bodies and shapes that are available in this simulation. Other settings in the simulation component is solver settings. So we can create a new asset, solver settings, and then we can see if we double click it, we can find more settings for the simulation. How many threads are being used in the physics simulation? The default is 4, and I don't see any reason for changing this. We can also enable warm starting for direct frictional contacts. And this is very useful when you're simulating robotics, where you're using contact friction to grasp objects. But we'll come back to that later on. And the rest of them are more in detail described in the AGX Dynamics user manual. So if you go here to the AGX Dynamics user manual, you can find more information about how to set this specific settings. I would recommend not changing them and just use the default. Finally, regarding the simulation component, we can also see that it has some options for exporting models. This can be very handy if something goes wrong in the simulation. What you can do then is you can enable this dump initial model, specify directory my scene.agx, and what will happen is when you start the simulation, a file will be written containing all the dynamic information in the scene. So whenever a bug has to be reported and you don't want to or cannot send the whole project, you can at least send this file that will contain only the rigid body, the shapes, and the constraints of the system, so that we can do some investigation to find out what's wrong with it. You can also, anytime during the simulation, output this file to disk, so you can, for example, start the simulation and simulate until a certain point in time, and then you can press output and write the current state of the simulation to a file, which you can then later on email us. There's a logging enabled here, available here. If you enable it and give it a file name, agx.log, it will create some information that might also be handy when we're doing some debugging. So if you get some problems, you can also send this log file to us. And that concludes the second tutorial of AGX Dynamics for Unity.